This is the second in a series of collision example videos. This is like the video we did previously, only in the previous video, mass 2, which is this train car, was not moving. In this case, I've allowed it to have a velocity that's to the right. So I have mass 1, this train car with a velocity to the right, v1 initial, this train car mass 2 with a velocity to the right, v2 initial, and then after they collide, because these are train cars and they have couplers, they're going to couple and they're going to move together as one. So because that happens, we can identify this as a perfectly inelastic. And we can say that we expect momentum to be conserved and kinetic energy not to be conserved. So now that I'm allowing M2 to move, I should say we've got some initial conditions that need to be satisfied if there's going to be a collision to begin with. If this is my setup, then V2 initial has got to be less than V1 initial. Think about it. If this one's moving faster than this one, there's not going to be a collision. So if you look at a system and you find that the second object over here is moving faster than this one, then there's no problem to solve. There won't be a condition. But assuming that I satisfy this condition, I look at the parameters and, okay, yeah, that'll work. So in other words, assuming I have an actual collision, I can solve this again with the conservation of momentum, which I already alluded to here. Conservation of momentum says this: total momentum of the system initially has got to equal total momentum of the system finally. I have again drawn a final velocity to the right of this coupled object. If I look at my momentum before the collision, the entirety of it is directed to the right. If I'm going to conserve it, then therefore the momentum after the collision will be directed to the right. That is part of the conservation of momentum. So I'm still pretty confident that my final velocity is to the right here. Same procedures I did before, only I won't have a term disappear. I'm going to sum up the total momentum before. It's going to be m1 v1 initial plus m2 v2 initial. That's my total momentum of my system, both objects, right? One object, two objects. And that's got to equal the total momentum afterwards. m1 plus m2 is the mass of my coupled object times v final. I don't have this term going away in this example because it's not zero, but I can still immediately solve for v final here. V final is going to be this: m1 v1 initial plus m2 v2 initial over m1 plus m2. You can do some algebra here to get the masses by themselves, or get the masses as a coefficient. I'm not going to. I'm going to leave it like this. I don't think there's any intuition we can really get here that we didn't get in the previous video. But I do want you to see that, what I want you to see is that the final velocity here is going to have to match up with the direction of the initial velocities. Because they're moving in the same direction, I've got a total momentum to the right, total momentum to the right afterwards. And it's a little harder to see, I still get something having to do with the ratio of the masses here. So the masses are playing a more and more critical role. They've been critical all semester. But the masses really determine what's going to happen here, how fast this final velocity is, and everything along those lines.